All right, folks, so let's dive into kind of brief introduction to compression design for both concrete and steel. So what I'll do is give you kind of a really general overview of concrete. When you take concrete design next year, we'll get way more into this. And then a fairly thorough intro on steel compression. Um, so anyway, some examples of failures in concrete columns. You can see these are both due to earthquakes. You can see the differences in behavior given the amount of ties. I think that's something we want to definitely take a close look at as we get into column design in concrete. In steel, oftentimes we get buckling, which is the dominant failure mode in steel columns. In this video, it's worth pulling up the PowerPoint and watching. Gives you a good feel for what column buckling looks like. So as we load columns along their length and compression, things tend to shorten and cross sections get a little fatter. Buckling is a major dominant failure mode. This would be single curvature. If you've sat there at a restaurant and played with your straw, you can kind of play around with what happens if you brace in the middle versus just braced at the ends. One of the things we need to look at is P delta effects in columns. So we have two types of these. One, P big delta, which considers um, this deflection up at the top, which is like the entire building moving. And then P little delta is the local deflection where the shape may change or deflect along its length rather than the entire building moving. As we get into more involved analyses, we can use RAM or similar software to capture both of these effects. Another thing we need to look at carefully is what are the boundary conditions of our columns doing? So a lot of times in column design, we may have different end conditions that will basically affect the buckling length. And so in some of these examples, you can see a fixed, and the effective length is basically half the original length. Kind of condensing that into a simple chart. We can use this depending on our boundary conditions. And you'll notice that these values are a little different than these. These are um, engineering values that we use that take into account the reality of the flexibility of the support. So because we don't have an infinitely stiff fixed end, if we had one in a column, there is some rotation either in the foundation or in the connection. So we're going to use a value a little bit more than 0.5. So for a normal pin column, we're going to have a K of 1. If we're pinned or fixed, 0.65, pin fixed, 0.8, and if we're fixed free, actually 2.1. So in this case, if you imagine the deflected shape comes all the way down to here as the length, that's why this is extra long. Okay, so looking at concrete design for concrete columns, we basically create what's called a interaction diagram. And we have two curves here. One's the nominal curve, and then one is the factored curve. So this curve in the dark line has the safety factor applied to it. So what happens is in concrete columns, if we get the moment and axial load, we plot that on this chart. So moments along the bottom here and axial force along the vertical. We just plot those intersections. And if the plot of that intersection falls within this curve, then we know we're safe. If it falls outside of the curve, then we're not safe. So these curves we develop based on strain conditions. And rather than get into all of this semester, I just want to give you a taste of it, just to get you excited for when you take concrete next semester, next year. So basically what we look at are points of different strain. So right here along the vertical with no moment, or pure compression. As we start working our way along the curve, here we have a point where we're zero tension and full compression, and then some portion of tension and compression. And then as we get to this point right here, we get to more pure bending, which is something familiar to you. And then as we come around to the tension side, we eventually end up in pure tension. So let's just look at point B right here. If we look at, so the cross section of our column here, the first thing we do is to say, okay, at this point, we're going to say we have, let's draw the strain distribution. So we're going to assume we have no strain in this bottom layer of bar, and then the concrete reaches a crushing strain of 0.003. So that should be somewhat familiar to you from concrete beams, that the crushing strain happens at 0.003. Based on this information, using similar triangles, we can find the strain in each subsequent layer of bar. Multiplying the strain by the modulus of elasticity, we can get the stress in the bar. And then multiplying each stress by the area of the bar, we can get a force in the bar. So these equations basically walk you through getting the strain, getting the force, or the stress, getting the force in the bar. And then what we can do is just sum forces to get axial capacity. So if I add the compressive force, the compressive resultant force, to the bar compressive forces, I can get my nominal axial capacity. So that's my vertical point, or my vertical place on this curve. And then if I do sum of moments, I can get flexural capacity. So similar to beams where we're summing moments. And in this case, let's see where we're summing about. So H2 over A2. So we're summing moments about the center line of this member, and just taking whatever forces we have times their moment arm to get the nominal capacity. And then we multiply by our strength reduction factor, which in this case is 0.65. Eventually that becomes larger than that, which helps us. So anyway, we basically use this concept to work our way around these different points based on these different strain conditions. And then we just connect the dots, apply phi factors, and then we're good to go. All right, because that is burly enough, we're going to kind of stop here and just talk about a few detailing things. So on concrete columns, generally we limit the area of the still in the column to 1%, and the code limits it to 8%, but actually 4% is more considered an upper bound economical limit. So generally, if you take your area of concrete, multiply it by somewhere between 0.01 and 0.04, that's a good starting place for the amount of reinforcing. Or maybe said a better way, once you do your concrete column design, if you check kind of this economic or functional limit, it's a good way to say this is a column that's buildable and is fairly economical. There's also requirements on the spacing of bars, both the lengthwise bars or longitudinal bars, as the code calls them, or crosswise bars. The code calls these transverse bars. Anyway, so this kind of summarizes the ACI requirements for column bar configurations. Okay, we kind of hinted at the beginning about column tie spacing. So in this case here, this is a same building, same hospital. This column was really heavily tied, and you can see that even though the cover has popped off the column, the concrete inside the core is still intact. So this still carries load. Whereas this one, you can see the spacing on the ties is so far apart. Most of the ties have popped, and that concrete inside of the rebar is really not load bearing anymore. So when we get into seismic design, the design of the members themselves still follows the same principles you've learned already. What's different is the detailing requirements to make sure this type of behavior happens rather than this. And that's the crux of seismic design. Okay, so let's jump over to still. The fundamental equation is pretty simple. It's the area times the critical buckling stress. Um, this critical buckling stress is given in these two equations, and it's a function of slenderness. So LC is that K factor we looked at earlier times the length, and then R is the radius of gyration. Often that is the radius of gyration about the y-axis. So we want to use the lowest RY or R value, and for wide flange columns, that's always RY. So if we take a look at this equation plotted, if you remember from mechanics of materials, Euler buckling gives us this curve, which is really great when you get to quite slender columns. But at some point, Euler overpredicts column strength, so it only is going to work for more slender columns. You can see the curve fit is fairly good, maybe up until 110 or beyond 110. From there, we need to get into these other equations, which honestly is what this here does. So this equation gives us more this range, and this equation is more an Euler fit, but you can see how this has the 0.877, which is why there's an offset in the curve. So anytime you're doing steel column design, Euler probably just isn't the greatest because at some point it just doesn't work anymore. All right, so in steel columns, we'll basically calc this LC over R. If it's less than this expression here, we can use this equation. If it's greater, we use this, and then both these equations have F sub E in it, which is actually very Euler. That is the Euler buckling equation. So that's where Euler fits into this whole thing. Okay, this chart here on your quiz, this will help you. So one of your questions in your quiz will actually refer to this. Basically, what I can do here is find the critical buckling stress times phi. So it would be this times phi for different strengths of steel. So yield strengths, 36 would be A36, 46 is the grade B tube, and then 50 is wide flanges. And then LC over R is given. So you can see it goes from 2 to 200. Anything over 200, the code doesn't let you do. And you can see the stresses get so low, it's really not worth it. So let's say I have a slenderness of 88, LC over R of 88. I can come here, come across, if I have a yield, say of 50 KSI, I have 25.5 kips per square inch of critical buckling stress. So if I were to multiply this 25.5 by the cross-sectional area of my column, then I get the axial compressive capacity of my column. The manual also has some real fantastic tables where I can get the axial compressive strength, either in allowable stress or LRFD. So let's say I have a 30-foot column, or LC over, just a 30-foot. So this is just the length. And say I have a W14 by 455, and I want to use LRFD values. I have a capacity of 4,120 kips. These tables are super great to actually go the other direction and say, I have a force in a column, say, of 6,200 kips. What column works? So let's say that column in particular was 19 feet, and I need 6,200 kips of capacity. I can see this is bigger than that. This is less, so this would be the first column in the 14 series that can carry that force. Um, so this is a great table to actually choose members from, because you can enter it with the load you need and then choose a member based on that. All right, oftentimes in columns we have axial force and bending force. We talked a little bit about this in mechanics. To handle that, the steel code gives us two equations which are dependent on the ratio of axial force to axial strength. So anything with a U under it, remember, is axial force or factored force, and anything with an N stands for nominal capacity. So if we have a fairly, or for that ratio is over 0.2, we'll use this equation where we're basically taking the ratio of strength or load to strength, moment to moment strength, moment in the other axis to moment strength. Add those up less than 1, then we know we have a safe column. And then just a slightly different equation if the axial stress ratio is fairly low. All right, a few examples. So here's a heavy brace frame example. You'll see the columns are called out in elevation. On some jobs, columns are called out in plan view or in schedules. If you do them in elevation, you have to show every grid line, so you can call out every column. That's actually my preference for drawings, but sometimes on commercial projects that becomes pretty tedious. All right, couple connection type. So here's a base plate, a heavy base plate with a heavy brace frame connection in it. Then a kind of a moderate column splice detail. All right, that's all we got there. As far as other resources, I've given you a still column example from one of my books, which basically will walk you step by step on how to calculate the loads on a column and then select the column and check it to make sure it's strong enough. So with that, I will see you in class to continue our discussions.